Welcome. In this video, I'm going to talk about neural networks and implement neural networks from scratch in C. So that brings us to two questions. Why do it in the first place? Like, why not use some good open source libraries like PyTorch or TensorFlow? Well, this is for educational purposes. We are trying to get our hands dirty with actually implementing the algorithms working behind the scenes in such big libraries. Now, in no way I'm saying that we are trying to imitate something that those libraries are doing. They're doing something way more complicated and way more optimized than what we are doing. We are basically trying to have a basic outlook of what these algorithms or these systems work with, right? So that's what is the purpose of this video. And secondly, why C? Now, we are using C because of one primary reason, that C is very basic programming language, right? C does not give us very handy shortcuts in syntax, or it does not give us a lot of abstraction. So we can work with fundamental stuff and get our work done. That's the reason we are using C for this project, okay? Without further ado, let's get started with the code. Now, the entire code I will be showing you in this video is available in my library CGL. Now, you can check that out in the description. I will be putting a GitHub link. Okay, now, before starting, I would like to say that if you are not familiar with the math of the neural networks or the equations behind the training of neural networks, go ahead and check this video by 3Blue1Brown, which explains in great detail the actual math behind the training and actual math behind the evaluation of the neural network, right? So I would be not covering those things in depth, though I would be talking about them lightly, but I would suggest go ahead and check that video before getting into this. So let's get started. Now, before we can actually start working with the neural network, we need to have a data structure to store the neural network, okay? Now, a lot of people might think we can just start having a data structure for the neuron, but we don't really need the data structure for a neuron, because what is a neuron in a neural network? A neuron is essentially a number, the activation value. So we don't really need data structure for a neuron. What we need actually is the layers. We can abstract these layers as individual data structures. Now, why? Because what is the actual thing we are trying to train in a neural network? The weights, right? So the weights are basically associated with layers, right? The weights connect to a layer, like a neurons of a particular layer. So we can group them up together. So let's say we have abstracted a layer. So for abstracting a layer, let's create a C data structure. So here we have got a simple neural network layer. So the first variable we have got inside that is the weights variable. So it's just a float array. Now, how is exactly we are arranging the weights? I'll come to that a bit later when we are actually trying to initialize stuff, right? So the next thing we have got in that layer is the activations array. Now, what exactly is the activations array? The values of the neurons that's going to be calculated will be stored in the activations array. Now, we don't really need this array. The purpose of keeping it here is basically we can just take that array and feed it to the next layer as input, and then we can just implement the feed forward algorithm, right? We could do it differently too, so it's optional for your implementation. Next, I've got an array for errors, right? Now, don't think of it right now, because we'll be talking more about it while we are talking about training the neural network. The next variable is the activation function. So that basically is a function for calculating the activations, right? Then we've got the activation function derivative. Now we'll be needing this again for training the neural network. So again, we'll talk about it a bit later while we are actually writing the code for the backpropagation based training. The next thing is the input count. That's the number of neurons in the previous layer, or the number of input activations this layer is going to expect. Then there is the output count, and then there is the weight, the number of weights that this layer has. Alright, so that's it for the layers data structure. The next thing we need is a data structure for storing the entire neural network. Now, for our case, it's going to be very simple. It's going to be just an array of layers that we just created, and a integer saying the number of layers. That's just we could just replace this with a layer number of layers, but I just want to keep track of the number of layers in there, so I'm just having an extra integer of them. So that's it. Now this is ideally not a neural network, because for implementing complex structures, complex architectures like skip connections and stuff, we actually need to have a total graph for the neural network. But we are just in this video, at least, we are trying to focus on a simple fully connected neural network, so we can just store that in an array. So that is all we need as data structures. We can store all the data of our neural network in these two data structures. Okay, so the next thing we're going to talk about is actually initializing the neural network and creating an object for the neural network. Okay, so first we have to create an object for the neural network that's going to store the layers. So that's what we are doing out here. We are using malloc to allocate the memory for that particular object, which is standard C syntax. Then we are just setting up the layer count in there. Now, how exactly are we passing the layer sizes out here? Now, the layer sizes is a list of integers. What does that mean? Actually have? It's actually having the number of neurons in each layer. Okay, it's the number of values in the layer sizes array is basically the layer count. Okay, so then we are actually allocating the array to store the pointers for the layers out here, which is again standard C stuff. Now, I'm not really checking whether malloc failed here or not, which is a good practice, which you should do, but we are going to skip that for simplicity's sake in our example. Okay, now the next thing is, for each layer we are actually going to initialize the layer. First, we are going to take the layer pointer and we'll get the pointer to that particular layer or object, and then we are just going to say that initializing the variables like the activation function derivative. By default, this initializes to the sigmoid activation function, which looks like something like this. Now, you can learn more about it again in some videos about this particular the math of the neural networks, but let's just say that we have got the sigmoid function. Now, we could use something like relu or any other function like tanh and stuff, but again, default is sigmoid, the simplest one, I guess. Then there is the input count. Now, if I is greater than 0, that is, if we are not dealing with the first layer, the first layer is basically the input layer, right? So input layer does not really need any inputs, because that's the activations in the input layer is actually what's going to be fed into the network. So if the value of I is 0 out here, that means it's the input layer, so our input count is basically 0, or like the value input count does not make any sense. But if it's greater than 1, then we are just assigning the input count from this like this variable out there, that is layer sizes I minus 1, because layer sizes 0 is basically the input count, like the first layer's input size. Okay, means layer size 0 will have the number of neurons in the first layer, so basically the layer input count of the ith layer would be the number of neurons in the previous layer. So it's basically we are doing I minus 1 out here, right? That's the input count. Next, we are having the output count. Output count is basically the number of neurons in the current layer, that is the layer sizes at the ith index. Then the weight count, basically weight count would be input count plus 1 times the output count. Now, why are we doing this in the first place? First of all, ideally it should be like you might think it's input count times output count, because we have got n like input count number of neurons in the previous layer and output count number of neurons in the next layer. So like we are connecting each of them with in the first layer with each of them in the second layer, so it should be input count times output count, but it's input count plus 1 times output count. Now, why is that? Now, in neural networks there is a concept called bias, right? Now, for biases, we can either, let's say, implement the bias logic separately, but out here what I did was I added another extra neuron in the input layers, right? And like in the input layer, and like set its value to 1 for all cases, okay, and its value is constant at 1, and the and we're just passing it to the natural neural network, right? We are not going to calculate its value with the help of the previous layer. It's going to be constantly 1, and that's going to act as a bias along with its own weight, right? We are multiplying it with its weight, and it's going to act as the bias. The next, we are initializing the memory for allocating the memory for the weights, the activations, and the errors. Again, we are setting the activation count in the output count, that is the number of neurons in the current layer, to be output count +1. That +1 is for the bias, same for the errors. So, and we're just returning the network. So that's basically how we are creating the neural network object, okay, creating and initializing stuff. Now here we are not exactly initializing the weights, so we need to initialize the weights of the neural network for it to at least be trainable, right? Because now it's containing garbage values, which can be anything, which kind of give us weird results for training, or will take huge time for training. So basically we need to randomize, we need to initialize the weights in some tame values, okay? So we've got a function for initializing the weights. So this is a function I call randomize weights function. So it takes the network and it takes two values, a minimum value and a maximum value, and creates sets the values of each weight in each layer to be a random number in that range. Pretty simple stuff, and that's how it's done, okay? The next thing is evaluation of the neural network, okay? So basically what you see in normal Python libraries, that is the predict function, okay? So what does this take? The neural network object, the input, the object, the input vector, that is the list of the input labels, or we can say the activations which will be used as the activations of the input layer or the 0th layer, the output or the output pointer, that's where we are the output we calculate is going to go, right? That's an output variable. Now what we are doing in this logic, first of all, we have got a neural network, a layer PR variable, which is taking the 0th layer, the first layer in the network, that is also the input layer, and the layer CR option, that is taking the second layer or the first hidden layer of the neural network, okay? Now then we are just copying the input variable, vector into the activations layer. So basically we are just feeding copying the value of it into the activations array, so that we can just use that in there, right? You can reuse the same code for all the layers. Then we are just setting the value of the bias in the activations layer of the first layer. So we're setting it to 1, as I said previously. Then we are looping, okay? We are looping from 1 to the layer count. This is the basic implementation of the feed forward algorithm, okay? Now from 1 to the layer to less than layer count. Why from 1? Because 0 is the input layer. We don't need to calculate its activation. So feed forward. Now layer PR holds the 0th layer, or we can say that the previous layer, and layer CR holds the current layer, okay? So inside the loop, we are looping from 0 to the output count. So this is the number of outputs in there, or the number of neurons in the current layer, okay? Now we have got a sum variable inside that. So now for each neuron, now we are looping through all the neurons. You can see the output count is the number of neurons, so we are looping through all the neurons here. So for each neuron, we initialize the sum variable to 0, and then what we do is we loop through all the neurons in the previous layer. We loop through all the neurons in the previous layer, multiply the value of that neuron times the corresponding weight. Now we are storing the weights in a particular order, we are multiplying it with k because times output count, because we are storing it in that particular order. Now we could, if you store the weights in a different order, we could also multiply it with j and add k. So that's totally dependent upon you and how you arrange it in your memory. But we are doing it like this out here. So we are calculating the sum. Now then we are passing this sum through the activation function. Then we are calculating the activation at the current neuron in the J, right? Let me just summarize it for you. We are looping through all the layers from the first layer, from the layer 1, because layer 0 is the input layer. So we are starting from the first hidden layer. Our layer PR variable is the previous layer, and layer current variable is the current layer, right? And we are looping through all the neurons in the current layer, and then for each neuron in the current layer, we are looping through all the neurons in the previous layer, and then actually calculating the product of the relevant weight that is connecting that neuron to the current neuron, and the activation of that particular neuron, or basically the value stored by that particular neuron. And after we calculate that sum, we're passing it to the activation function and calculating the activation of the current neuron. Okay, after we've calculated the activation of the current neuron, basically the job is mostly done. Next, we are moving outside the loop. That is, we have moved through all the neurons of the current layer, and then we are setting the activation of the current layer, the bias of the current layer to be 1. Again, output as we initialized in the previous create function, the size of activation is output count plus 1. So at index output count is the index for the bias, so we set that to 1. Okay, and after that we are just setting layer PR equals to layer CR. That is, the previous layer is now the current layer. The current layer becomes the previous layer, and we increase the current layer to 1, add 1 to the current layer. Okay, so move on to the next layer, and this repeats itself, and we feed forward the data from the previous layer, calculate the activations of the current layer, and move on, make the current layer the previous layer and move on to the next layer and calculate its activations till we move on to the last layer. And at the last layer, when we calculate the activations, we have already calculated the activations or the outputs of the neural network which we are trying to predict. Okay, and after that we have already the activations of the layer PR. Now layer PR, after the loop, after we have exited the loop of the main feed forward algorithm, the layer PR would be the last layer we have, right? So we are just copying that, though its activations, into the output variable, and that's basically our predict function or the evaluate function of our neural network. So it's just few lines of code, and it's so simple that we're calculating we are evaluating a neural network this way. Okay, alright, so now let's move on to the most interesting yet most of the complex part of this entire thing, that is the training function. Now we have implemented the training function for the neural network as a single compact function. So let's get into that. First, it takes the neural network object as expected. Then it takes the input, that is the test input or the training X, what you call in normal common terminology. Then there is the output, which is basically the test label, training labels, right? And there is the learning rate. Now we use stochastic gradient descent for the training, so we'll be taking only one input and one output, a single input and a single output at a single time, and then train based on that, rather than taking batches of inputs and outputs. I want to keep the things pretty simple and not try to optimize a lot and get things complicated. All right. So first thing we do in this training set is calculate the output. Okay, we are just calculating the evaluating the neural network with the evaluate function we just saw. Now why are we passing null in the output section? Because the output is already going to be present in the layer activations array of the last layer. So why why should we allocate another output variable, output vector for storing that, right? So it's already there, so we're just passing in null and we're calculating the output. So we're just running the feed forward algorithm for that particular input. Okay, next is basically we are again taking the layer PR and layer CR. Now layer PR and layer CR are pretty different from what we saw in the evaluate loop, because here we are in the evaluate loop, what we did was backpropagation, but what we did was the feed forward algorithm. But here what we are doing is backpropagation, right? So in the feed forward algorithm, we started from the first layer and moved on forward, right? But here what we do is we take the last layer and move backwards. Okay, so the layer PR is the last layer. So layer a.layers is basically the pointer to the first layer, that is the input layer. So plus layer count is going to go outside the layer, so it's beyond the last layer, so we do -1. So basically we choose the last layer. Next, we just take in the layer PR -1 to be the layer CR. So layer previous is the last layer. That is basically the output layer. Now we don't need to change, like layer PR is the output layer, right? Now layer CR is the current layer, and that is layer PR -1. That is the penultimate layer at this place out here. Okay. So first we need to calculate the errors for the last layer. We are doing it separately in this loop. What we are doing is, for every single layer in the last layer, that is the output layer, or what we have in layer PR pointer, for every single neuron, again output count is the number of neuron, as you might know already. For every single layer, we are just calculating the errors. Now it's not really the error term, we are just taking the output I, that is the test label, or what we can say y hat, minus the layer activations at the current index of the at the current neuron, that is y. So we are just doing y hat minus y times the derivative of the activation function. Now why exactly that? Now to better understand why we are doing this out here, I should recommend you go ahead and watch the video by 3 Blue 1 Brown regarding the math behind neural networks, because we are taking something from that thing out here. So what exactly we are doing is, we are eating the, let's say, how a neural, let's talk about basics of the equations of the neural network. Okay, so the gradient descent algorithm basically applies, let's say, for the ith for a particular weight, we need to, how can we edit it, how can we nudge it to be more accurate, right? Now I'm going to give a very basic and shallow explanation of that. So again, for explanation in depth, you go ahead and check that video. Okay, so what exactly it does is, it takes the current value of the weight, subtracts or adds, or let's say subtract a particular value. What is that value? It's a learning rate, a constant, that is learning rate, times del, the partial derivative of the cost function, that is, we can choose a cost function with respect to that particular weight we are trying to change, that particular weight we are trying to nudge. Okay, right, now that's the basic idea. Now let's try to simplify this further. We are trying to change the value of the weight I, let's say weight I, by adding or subtracting a value, that is del C by del W, that is the partial derivative of the cost function with respect to that particular weight, times a learning rate. Now why are we having a learning rate? That's just so that it just doesn't make sudden jumps or sudden huge changes which might affect the stability of training. So usually learning rate is something of very small value, like 0.01 or 0.03, so that it just trains slowly and smoothly. Okay, now this learning rate is a hyperparameter, a parameter which you should tweak to see what value gives us a better, faster training and better quality of training. Again, this is something we have to find out with trial and error, and basically something different for each network and each problem we are trying to solve. Okay, back to the topic. The del C by del W term, now how are we calculating that? Now del C by del W is, what exactly does it signify? It signifies the change in C by a change in W. What does that mean? When we are tweaking W, we are changing W by a bit, the value of C changes by a bit, right? Because somehow, when we are calculating the value of C, this W plays a role. Okay, so the value of C is somehow being affected by the value of W. That's the basic idea. So we are calculating the change in C with respect to W. Now we cannot actually calculate the derivative of C with respect to W directly. So we use something called the chain rule. So we can write del C by del W as del A by del W times del C by del A. Now del A, what is A? A is basically the activation of that particular layer we are trying to change. Now C is the cost function, right? Cost function can be anything. There are several cost functions out there, like the cross entropy loss function. There are several cost functions, loss functions, right? Now basically we are using something called the mean square cost function. Basically we are trying to the cost of the error in our network is basically sum of all the let's say W sorry, a y hat minus y whole square. That is the sum of all that is basically our cost, or that the error in our network. Okay, the target output minus the output our network generated, the square of that. That is the mean square error function. Okay, the cost, our cost function. Right, now we are basically and since we are calculating it for a lot of vector variables, we have to sum it up and create calculate an average for that. Now that's let's not discuss about that. Let's talk about the basics. So we're calculating the cost function like that. Now what, like, we can say that again, as I said, the del C by del W can be rewritten as del A by del W times del C by del A. Now del C by del A, what is A? A is basically Y, because A is the value of the activation, right? And for the last layer, we can say that the value of the activation is basically value of the Y, right? So we can see that del C, now C, let's replace C, let's say Y hat minus Y whole square. So del Y hat minus Y whole square by del Y, right? A can be said to be Y for this case. So what is that? Del y hat minus y whole square by del y. So we can say that it's minus 2 y hat minus y, right? Now we can just ignore the minus 2 for now, because let's say we can ignore the constants for now, because well, you know, we are multiplying with the learning rate anyway, so like the constants can be ignored for now. We just need the value y hat minus y. That makes a lot of sense, right, for here. So the derivative of del C by del A is y hat minus y. That now del C by del W is del C by del A times del A by del W. Right? Del C by del A is y hat minus y. We can calculate it like that. Let's approximate it like that, right? Times del A by del W. How can we calculate that? Now del A by del W, what is that? Del A. Del A is the activation, right? Now we can write that as del A by del Z times del Z by del W. What exactly is Z? Z is something, the sum we calculated. You know, remember, while we calculated the evaluated function, in the evaluate function, we calculated a sum and passed that sum to the activation function, right? So that sum is del Z, right? So we can say that del A by del W can be rewritten using the chain rule as del A by del Z times del Z by del W. Now del A by del Z, well, del A by del Z, well, what is that? That is the derivative of the activation function with respect to the function itself, right? With respect to the value that we are passing into the activation function. Okay, that's interesting, because that's basically the derivative of our activation function. Okay, so that's why we are multiplying using the derivative of the activation function out here. So del A by del Z is basically the derivative of the activation function. Now then we have last thing left is del Z by del W. Okay, sorry, del Z by del W. Yeah, what exactly is del Z by del W? So the derivative of del Z by del A, the derivative of the value before the activation that we have stored in the sum variable, we calculated in the sum with respect to the weight. How exactly is that? What exactly is that? Now, if we see what exactly is the sum, it's the activation of the previous layer at the index I, then a weight, then the activation at another index I, then the weight. It's a sum like that, right? For a particular weight, if we are trying to calculate the derivative, partial derivative with respect to a particular weight, and letting all the others be constant, it's basically the activation at that particular corresponding to that particular weight, right? The activation corresponding to that particular weight. That's the error term, alright? That's the derivative. So our final equation for nudging the value of the weight comes down to the del A, like the equation in the partial derivatives would be del Z by del W times del A by del Z times del C by del A. So del Z by del W is the weight times the partial, not the weight, just the activation of the previous layer corresponding to that particular weight, that value, activation value, times the value of that particular then there is the del A by del Z, which is the derivative of the activation function. Then there is the del C by del Z, del C by del A, that is y hat minus y, the prediction minus the activation value, right? That's for the last layer. Let's just consider for the last layer. We can just take this similar idea and propagate that backwards, right? Now we can calculate the error for the previous layers in a similar way, right? The the value or the error is getting divided into two parts. One we are using to nudge the value of the weights of the current layer, and one we are just moving on to the previous layer as the errors of the previous layer, so you can nudge the weights of that layer and then moving it back again. So that's the basic idea of backpropagation. We are propagating the errors backwards through the layers of the neural network, right? We're propagating the errors. That's the basic idea of backpropagation. Now, we calculated the errors of the last layer separately out here. The next thing we do is basically the basic idea of backpropagation. All right. Why are we multiplying? One thing before moving on is, why are we multiplying the derivative of the activation function and the subtract y hat minus y value only, and not the last value? Because this error is going to be used two places, right? We're going to derive one value that's going to be used to nudge the weights of the current layer, and one value that's going to be passed back, let's propagate it backwards into the layer before, right? So in the equation, things are going to change a bit with respect to that. What I mean is, in case of when we are changing the weight of the current layer, we need to find the derivative with respect to w, right? With respect to w. So that last value would be del z by del w. So in that case, value would be the x of the x value or the activation value of the previous layer at that particular index, right, corresponding to that particular weight. Now we will multiply it with this error value with that, and then subtract it from the weight, and multiply it with a learning rate, and then nudge the weight of the current layer. And how can we propagate the error backwards, right? The error is there will be an error corresponding to something at the for a previous layer neuron. There has to be an error, right? Error, the size of error is same as the size of number of neurons, right? For each neuron there is an error. So the previous layer should also have error. So we need to propagate the error backwards. So that's what we are going to do in the next loop. Now, let me just give the basic mathematical idea again. So basically, while propagating the error backwards, we are just taking rather than taking del z by del x, del w at that particular index, we are taking del z by del x, right? We're checking how the weight or how the cost function is. In this case, we define the initial formula or the initial idea was del c by del w, right? So in this case, the idea will change to del c by del x. Now this x is basically the network, the neuron we are trying to, the activation of the neuron we are trying to calculate the error for, the neuron in the previous layer. And we're trying to check how is the value of that neuron is affecting the, let's say, the cost function, right? So we're trying to calculate that. Now we're going to calculate the change with respect to that. Now again, if you just think about it, apply the same logic as we did with the weight, you can see again this rest of our part, the del c by del x, let's call it x. So del c by del x, again, if you can separate out as del c by del a times del a by del z, again del z by del x. Now del c by del a times del z by del a by del z is a constant part that is being used in both for calculating the nudging the weights as well as calculating the error that will be propagated backwards, right? Now there is one thing to be aware of, right? We are calculating the error in the x with, let's say, del a, at the end we are just changing from del z by del w to del z by del x, but there is a big but out here, that is, we also have to take note that that particular neuron is not just affecting one single output neuron in the next layer, but also all the output neurons in the next layer, right? So we need to calculate this value for all the output neurons, right? So we are just going to calculate this value with respect to all the values in this error variable, right? This error variable contains the del c by del z, del c by del a times del a by del z. So that, we have to take in note all the this value for all the output neurons in the next layer for calculating the error in the previous layer. Now that's what we are doing in next part. So we are moving on from the like the last like the penultimate layer till the like initial layer, till the 0th layer, right? The penultimate layer, because the last layer is the output layer, and layer count -2 is the penultimate layer, right? For that layer, now layer CR out here is basically, as we saw previously, is the penultimate layer, and layer PR is basically the last layer. Okay, so we are dealing with the layer CR. First of all, we are in this loop. We are basically propagating the errors backward. We are not nudging the weights now. We will do that in a separate loop down below this. First, we are just propagating the error backward. This is the basic this is the core of backpropagation, right? So we are looping through all the neurons in the previous layer, that is layer CR, and here we are basically doing this, that is error of the current output neuron, like error at the error of the current output neuron. We are looping through all the neurons in the previous layer. So what I mean in the previous layer is the current layer. Now the previous layer is the last layer, and the current layer is the penultimate layer at the first case. So we are looping through all the neurons in the penultimate layer and calculating or backpropagating the error from the last layer. We calculated the errors of the last layer previously in the layer PR out there, so we are propagating the error backwards to the current layer. How are we doing that? You know, the error of the current layer, again, as I said, is the sum of the errors of error times the del z by del x. Now del z by del x, what is that? That is the weight. That is the weight value for that, corresponding to that connection, right? Now because again del z by del x is the value of itself, and del x itself, and del z by del x is weight value. Okay, so the value of the weight, we're multiplying the error with the value of the weight, error of the next layer with the value of the weight, times the derivative of the current layer, of the activations of the current layer, okay, the current neuron. Okay, so we are just looping through, like here we are trying to sum up. We are just as I say, like initialize a variable called sum with 0, and then just sum up all the error times weight value. Again, this error is the one we calculated previously. We are just summing up all the error times weight value. Again, we are multiplying it with weights, that is the last term, that is del z by del x, and we're just multiplying and calculating the sum, that is the sigma out there, and then we are just updating the errors of the current layer. Okay, that's the backpropagation. Now next we are just telling the previous layer to be the current layer. Again, that similar thing we did in the feed forward, but here rather than setting current layer to the next layer, that is like adding one, we're just subtracting one, because we are moving backwards. We are like going backpropagation, right? So that's the part about backpropagation. We have already propagated. Now we are just in the next iteration, we're just going to the next layer, moving on to the next layer, and then propagating it further till we go to the initial layer. We are done with propagating the errors backwards. Okay, the next thing we need to do is basically calculate, nudge the values of the weights, so that we can actually train the neural network, right? We've got the errors for each layer. We have propagated all the errors. Now we are training the weights. Now we could do the both of them together, but for again simplicity's sake, I separated out into two parts. Basically, again, we set layer PR to be the layer 0, that is the input layer. We don't really need to change the values of the weights of the input layer, because the input layer does not have any weights. Then we have got the layer CR. Layer CR is the layer PR plus 1, that is the current layer of the first hidden layer. Then we are moving on from, again, like the feed forward algorithm, we are moving from the first hidden layer to the last layer. For each layer, for each neuron in the current, for looping through for each neuron in the current layer, and we are basically nudging for each weight, we are basically nudging the value of the weight by the simple formula of the gradient descent algorithm, that is learning rate times the activation times the error. Now again said that the activation out here is again the del z by del w, right? Del z by del w is the x, so x out here is the activation, so x, the activation times the error, right? We are nudging the weights. Now we are adding it out here. We can do subtract, I guess, too. Then we are like learning rate is a constant, so again this does not matter, because we can obviously configure that with the learning rate. We can make a negative learning rate so that the thing would be like equivalent to subtraction, right? Again, that's something we should test out with and play with to find what is more suitable. Again, we're just updating the value of layer PR and moving layer CR to the next one. Now this is basically something similar to the feed forward algorithm. We are basically updating the weights. Now we could do that along with backpropagation, but I did it like that in a separate loop because this kind of makes things separate and easier to understand, because this is really a complicated algorithm. I would say that for now, just pause the video and just think about what we did in the whole process, and what exactly were we trying to achieve and how were we able to achieve that. Try to think why we had every single line of code and why we did that, right? Also, you could just rewatch the past 2-3 minutes to get a better idea. Now again, I would say the mathematical part, I tried to my best to explain it, but again, I would suggest watching 3 Blue 1 Brown's video. He explains it visually, which is pretty good for these types of things, right? So that's basically it for our training the neural network. Lastly, this is not really important part, but again important for code practices, that is destroying the object we created, since it's C, we need to free the memory. So this is the code. I won't explain it much, because if you are familiar with C, you can just see and understand what's going on. We're just going looping through all the layers, and basically whatever we allocated previously, we're just freeing that by calling free. Now that's basically it about the main algorithm of the neural network. Now let's see it in action. Okay, let's try and use it in a particular scenario, right? Let's say we are trying to create a neural network. Let's say for a very simple task. I'm not going to deal with a lot of magic data sets. I have a project where I created a OCR, or simple handwritten digit recognizer with this neural network. I'll put a link to that in the description. Also, I guess you can see it on screen now. Well, but let's do a more simple and basic example. We'll train the neural network to replicate the XOR operation. This is a very popular thing for testing neural networks, I guess. So we'll use it for simulating the XOR operation. Now let's see. We have got a simple neural network. Our layer sizes, first of all, it's going to be a simple int array. We are going to have 2 inputs. That is the we're doing XOR of 2 variables, and okay, so we have got our neural network will have 5 layers. Okay, first is the two input layer with 2 inputs. Then we have got a first hidden layer with 5 neurons. Then we have got a hidden layer with 7 neurons. Then we have got another hidden layer with 5 neurons, and then we've got a single output layer that is going to be 0 or 1. Now we could do 2 output layers, and that's up to you, right? And then we are basically creating our neural network with a simple function, neural network create. Then we are basically initializing weights by calling randomize weights function, as we saw. Then we've got our training and test data sets. Now you can figure out what this is, the basic XOR output. And also we have got a float array with single size for these, for testing out thing. Now in this output code, I'm just printing out the value of what the network predicts before training first. Then I am training it for some particular number of iterations. I also give the option to pass in the number of iterations as the parameters to the command line arguments. And then basically I'm just training the neural network with that many iterations, and basically index is modulo 4, or a random number modulo 4. Basically it's just taking a random training example and basically training based on that. And we are passing in a learning rate of 0.1. Now I didn't really experiment much with this because this is a simple problem and we want to test the neural network whether it's working or not. Alright, so after that we are just printing out the results after training and basically destroying the neural network. That's simple. So let's see the output. Alright, okay, as you can see, with about these many iterations, these many training iterations, we can see we are getting something really cool. That is, see the value where it is, both values are same, where it's supposed to be 1, it's 0.99, which is pretty close, and the other cases it's 0.003, and I guess it's a pretty good network, right? We can round them off and get the accurate results. Now I guess it's a pretty good network, right? Now Again, this is not something optimized, or not something that's for production. This is something we just did to learn something more about neural networks, learn something more about C, and basically enjoying ourselves in programming. Right now, this has to be a fun project for someone who enjoys implementing things, who enjoys learning how things work from a very ground up level, right? So I hope you enjoyed this video, and for more videos like this, I do make things like that often. So please subscribe to the channel and like the video, and thank you for watching.